Can you see the slides now?
Yes, sir.
Okay.
Yes,
Okay.
sir.
So,
Yes, sir.
let's begin. Yesterday I basically give you a very brief introduction to the Maxwell equations and the related things. I'm just I mean quickly going through the slides. So these are basically historical development that I touched upon, and then I have talked about Maxwell's equations. These four equations. Now, one thing I forgot to discuss in yesterday's class, that if you look at these four equations, this equation is very special. That is the modified Ampere's law, which basically came from Maxwell. This second part, this displacement current density. But can you tell me that see, so many pioneer experimental physicists were involved in the development of the subject, but none of them were able to measure this displacement current density in any experimental setup in their labs. So what could be the possible reason? I mean, why this has to be predicted predicted theoretically, and then I mean Maxwell, because this purely came from symmetry. Maxwell's predicted this term should be there, otherwise this law is not complete. But it was not measured experimentally by any of the physicists like Oersted, Ampere, Faraday. All of them were very great experimental physicists. So what could be the reason? Why it is so difficult to measure this displacement current? You see, if you look at this term carefully, you can see there is a term del E del T. Now imagine a circuit which includes a capacitor and some say AC source providing some voltage V equal to say V0 sine omega t. Now inside the capacitor, suppose it's an empty space, there is no charge there. So electric charge are getting accumulated in the plates of the capacitor, and since it's a sinusoidal voltage, so direction of the electric field will change in every cycle. Now if you look at this situation carefully, what do you expect from this term del E del T? So V equal to V0 cos omega t, right? Now, what is the relationship between electric field and this applied voltage V? There is linear relationship, right? Right? E and V are linearly related because E equal to dV dr. So basically, you can write E equal to V by d here. D is the distance between the two plates of the capacitor. And if V equal to V0 cos omega t, that means del E del T term, this del E del T term will throw an extra term omega in this term, right? If I take a derivative of E, which is basically so E equal to V by d and V equal to V0 cos omega t. So if I take a different time derivative of that, I will get an omega term here. So omega multiplied by mu 0 epsilon 0. Now what is mu 0 epsilon 0? We have already seen that mu 0 epsilon 0 is nothing but 1 by square of the speed of light, right? 1 by c square. Now omega divided by c square. Now tell me what is the frequency range that we use in our laboratory or home appliances. Right? The AC that we use in our home has a frequency of around 60 hertz, right? And that is divided by c square. C is the speed of light, 3 into 10 to the power 8 square. So 3, that means 9 into 10 power 16. So 60 divided by 9 into 10 to the power 16. It will be extremely negligible if you use the kind of frequency that we use in our experimental setups in laboratory. You cannot really measure this, right? It's very difficult to measure. But what happens in case of light? You see the frequency of light. If you look at the value of the frequency, say optical light or say radio or gamma, that omega and the speed of then this omega by c square term will be something which you cannot ignore, like you have ignored in your laboratory setups. So that's why it was very difficult to measure. So displacement current was not measured by anyone before Maxwell. So it was predicted theoretically, and this was the most important contribution of Maxwell, because it led to the Maxwell's equation, which gave us a complete picture, or rather to say, it's giving us the main tools which can explain all the electromagnetic phenomena in nature. So we have discussed about these four laws. I am not going back there. So, and then we have seen that if you go to the free space where there is no free charge density or free current density, The Maxwell's equations are looks like this, which can be easily converted to wave equation, which basically tells us that electromagnetic waves can exist in empty space, and they can propagate at the speed of light, that is 3 into 10 to the power 8 meter per second. And we can write down the waves in terms of plane wave solutions, where the waves have a complex amplitude because it incorporates the phase e to the power I delta inside them. K is the wave vector, omega is the frequency, and they have a transverse nature, that is electric field, magnetic field, and the propagation wave vector are mutually orthogonal to each other, and electric field and magnetic field are in phase with each other. Those things has been discussed. Then we talked about the energy density, flux density of electromagnetic waves, because they can carry energy from one place to other, which can be expressed in terms of Poynting vector. And also we have discussed that the electromagnetic waves can transport momentum, and this can be quantified in terms of the Maxwell stress tensor Tij, written in this way. Okay, so someone asked me how one can arrive at this expression. Maybe I can discuss this in a separate class. Now, let us look at the equations in matter. So we have written them. E and B now goes to D and H, because a material can have property. It can be dielectric, so, or a combination of a dielectric and metal. So there can be free charge density and as well as bound charge density, free current density as well as bound current density. And if you take into account all those terms, then electric field has to be written in terms of the electric displacement vector D, and H is the magnetic intensity. And these are the relationship between D and E and H and D, where T is polarization, M is magnetization. So these are basically general equations of Maxwell's in matter. And then if we assume that there are no free charges or free current in the medium, then simply since there are no free current, no free charge density, so this will be 0, J will be 0, so simply put 0 there. And then if we assume that the medium is linear, that means D and E can be connected in this fashion, and B and H can be written in this fashion, then you can simplify this equation further and write D in terms of E and B in terms of this. These two equations remain same. D in terms of E. So these are the Maxwell's equation in a linear homogeneous medium where there are no free charge density and no free current density. So once we have these equations in matter, we can easily again combine these equations into two wave equations, just like the wave equation in free space. 1 minute. And we can see that we again have this plane wave cell solutions which represent electromagnetic waves, but only difference is that here the electromagnetic wave will propagate with a different speed than its speed in vacuum. So now V will be 1 over square root of mu times epsilon. Now mu and epsilon are basically property of the material that we have taken here. So it will depend on the medium, so speed will vary depending on the medium. Okay. Now, so all these equations are in differential form. You see, there I can also write down Maxwell's equations in integral form. So Gauss's law can be written in this form, where basically what is the picture? It's the same. You have a charge density, maybe you have both free charge density and bound current density, and you enclose that charge density by some surface, any closed surface, and if you integrate the flux of D across that closed surface, you get back the free charge density. Okay, fine. Again, if you do this closed surface integral for B, you get 0. 1 minute. Some of you are sending message probably. Is there any problem? মানে কি শুনতে পাচ্ছো সবাই? হ্যালো, শোনা যাচ্ছে?
হ্যাঁ স্যার শোনা যাচ্ছে।
না, আমি আসলে প্রেজেন্টেশন মোডে আছি, আমি আর ব্যাক করছি না। মানে কেউ যদি জয়েন করতে চাও তাহলে আমাকে আবার ফিরে যেতে হবে। দাঁড়াও দেখি 1 মিনিট। কেউ যদি জয়েন করতে চায়, let me see. Someone is trying to okay, admit Ramit. Okay, Ramit জয়েন করেছো? হ্যালো
হ্যাঁ
হ্যালো,
স্যার, হ্যাঁ স্যার, হ্যাঁ স্যার, হ্যাঁ স্যার।
হ্যাঁ 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 হ্যাঁ, আসলে আমি প্রেজেন্টেশন মোডে চলে গেলে তোমাদের মেসেজ কিছু দেখতে পাচ্ছি না, তোমার টাইপ করলেও আমি সেখানে বারবার গিয়ে ব্যাক করে গিয়ে মেসেজ পড়াটা সম্ভব নয়, তাহলে আমাকে মানে প্রেজেন্টেশন থামিয়ে দিয়ে মেসেজ পড়তে হবে, কারণ দেখছি 21টা মেসেজ দেখতে পাচ্ছি এখানে আমি, রাইট? সো ইট ইজ ভেরি ডিফিকাল্ট টু বেসিক্যালি রিড মেসেজ অ্যান্ড দেন, তাহলে একটা হিউজ অ্যামাউন্ট অফ সময় মেসেজ পড়তে চলে যাবে। তুমি যদি জয়েন করতে না পেরে থাকো, আমাকে হোয়াটসঅ্যাপে একটা মেসেজ পাঠিয়ে দেবে, তাহলে আমি ওখান থেকে দেখে ব্যাক করে গিয়ে অ্যাডমিট করে নেবো। কিন্তু চেষ্টা করো 5 মিনিট মধ্যে, মানে ক্লাস শুরু হওয়ার 5 মিনিটের মধ্যে জয়েন করে যাওয়ার। আমি বুঝতে পারছি তোমাদের হয়তো সবার নেটওয়ার্ক স্পিড সমান থাকে না, সুতরাং এটা বলা যায় না, এটা একটা প্রবলেম, বাট চেষ্টা করো আর কি যে 5 মিনিটের মধ্যে জয়েন করে যাওয়ার। ফাইন। আদারওয়াইজ মানে কি বলেছো, এটা টাইপোগ্রাফিক্যাল মিস্টেক, ইউ আর রাইট রাইট রাইট, বিকজ ইউ সি what he is saying is correct, because when I write in terms of the differential, then you have a row, right? এটা টাইপোগ্রাফি খুব তাড়াতাড়ি করছি, স্লাইড গুলো একদিন দুদিনের মধ্যে তাড়াহুড়ো করে টাইপ করা, বুঝতে পারছো? মিস করি, ঠিকই বলেছো, হ্যাঁ কারেক্ট কারেক্ট, ঠিকই বলেছো, ঠিকই, এটা কিউ ফ্রি হবে, রাইট? কারণ এটা ইন্টিগ্রাল ফর্মটা আছে, আমি ডিফারেন্সিয়াল ফর্মে যেটা ছিল ওটাই লিখে দিয়েছি, চেঞ্জ করার সময় নোট করিনি। ফাইন, কারেক্ট, সো দিস উইল বি কারেক্টেড, গুড। So and now the third one is basically E dot, which is Faraday's law. You take line integral if you look at them, this is a closed loop integral, right? So we have taken a loop around which we are taking basically integral of E, which is nothing but the EMF, right? E det. And now what is this? Can you tell me what is this? B dot NDS. This is a surface integral, but which surface? Which surface? Same happens for the fourth equation. If you look at this, and if I write this in integral form, H dot dl is I free enclosed, right? Here I have not done the mistake, right? This is I free. This is not I free enclosed, and here what is this? This is del t d dot nds. So this is again a surface integral. This is a integral along a closed loop, and this is a surface integral. So the integrations are over any closed surface in the first equation. এই ইকুয়েশনটাতে ইন্টিগ্রাল যখন নিচ্ছি, এটা ক্লোজ সারফেস নিচ্ছি, বাট দ্য লাস্ট টু ইকুয়েশন যদি ভালো করে দেখো এই দুটো, the integrations are over any open surface. These are not closed surface, open surface bounded by the closed loop in these two equations. So we have a closed loop here, যার অ্যারাউন্ডে আমরা এর ইন্টিগ্রাল নিচ্ছি বা এইচ এর ইন্টিগ্রাল নিচ্ছি, সেই লুপটা any open surface attached to that closed loop is a varied loop. You can take any surface, right? You can take any surface attached to that open loop and integrate these right hand side equations, right? D dot nds or b dot nds to get a to balance this two sides. So this is the important thing, because this actually once this ambiguity about the surface becomes clear, you can understand the displacement current term, because this is the reason why Ampere missed this displacement current term. Because look at this example. I have taken this picture from Griffith's book. You see this is a plain parallel capacitor. So two plates are there and connected to some source. Okay, it can be AC source as well. So this is a source, and the current is flowing, and this is an empty space here. Now imagine a point here, somewhere here. So it's a point P at a distance, say R, from this wire. Now if I ask you what is the magnetic field there, you can easily tell me that magnetic field is mu naught I divided by 2 pi R, because you have already learned by using Biot-Savart's law how to calculate magnetic field near a current carrying wire. So B will be mu naught I by 2 pi R. Now if you go back to Ampere's law, which tells us that B dot dl along a closed loop will be mu naught I. So here I am using a circle, so basically B will be mu naught I by 2 pi R. You can get the same result by using Ampere's law. Now again, see, if I write down the Ampere's law in integral form like this, you see, here I have written it in terms of h. Again, they are same thing because they are only factor of mu there. So b dot l dl will be mu naught times I, and I can be written as j dot n ds in terms of current density, right? So this current can be written in terms of current density. Now this j dot n ds must be across some surface, and that surface, that surface, which surface? That's the question. Which surface? You see, if I take this surface, this flat surface, this shaded region, this black gray region here, suppose this is the surface. So Ampere's law tells us that if you take a line integral of b along a closed path, then it will be equal to mu naught times the current which is poking through the surface, which is attached to that open this closed loop, right? I'm repeating again, this b dot dl along a closed path will be mu naught times the current which is poking through an open surface which is attached to that closed loop. Now you see, you can choose a different surface attached to that closed loop. Suppose in this case you take this surface, then we are perfectly fine, because then b will be mu naught I by 2 pi r. But suppose forget about this shaded region, I am choosing a balloon like surface attached to that, say, closed loop like this. This surface is going to the capacitor, right? Now if you try to apply Ampere's law, you get b dot dl is equal to mu naught and integral over basically j dot n ds if you take current density or mu naught I, say. Now inside the capacitor you do not have any current, it's an empty space, there are no free charges, so naturally you get an answer equal to 0. So these two surface gives two different result. If you use same Ampere's law to calculate magnetic field at this point P by using two different surface, you get two different results. In one case you get mu naught I by 2 pi r, in another surface you get 0. So this is the ambiguity, because the surface is not well defined. Which surface? So here, because the law tells us that it can be any surface, and if you are trying to take any surface, we are getting ambiguous results. So that's why you see Maxwell's thought that maybe there is nothing wrong, is because you can choose any surface, that's fine, but maybe we are missing some terms in that equation which are not included in Ampere's law. So you see there are no free charges here, but if you look at this region, because if you suppose I put a source here, AC or DC, whatever, AC source suppose here, so then charge will be continuously accumulating here. Okay, if I put a AC source here, it's a battery shown here. If I put AC source, charge will be continuously accumulating on the surface, and the polarity of the electric field will be change with time. So in one half this will be along this direction, then in other half this will be in the so direction of is changing. Also the charge is amount of charge is changing, so electric field is changing. And what is electric field near a charged uniformly charged sheet? It is sigma by epsilon naught. Right. Suppose this is a square plate. So what is the electric field? So what is sigma? Charge density. It is total charge divided by the area. So suppose the charge which is getting accumulated is Q3. Suppose QF or Q divided by R square. Suppose capital R is the dimension of the plate. So Q by R square. Q by R square is the charge density. So the electric field near this plate will be Q by sigma epsilon naught into R square. That's the electric field near this plate. Now Q is changing because charge is getting accumulated, so it is changing with time. And if you go back to this formula, see here, if I look at this equation, so basically this is d epsilon E. Suppose I put epsilon outside, epsilon naught, so this is a del E del T. And what is a del E del T? If I take a derivative of E with respect to time, you see I told you that E is equal to Q by epsilon naught R square. So del Q del T, which is nothing but current. So del Q del T is current, and there is in the denominator epsilon naught into R square. Now you see, if you integrate over the area, there will be R square here. So that R square and the R square in the denominator will get cancelled, and there is epsilon here, right? Epsilon naught here. And you see, since I have written this in terms of d, so this will throw an epsilon naught outside, so that denominator will get cancelled. Denominator will get cancelled. So it will be simply basically so del E del T will become R square gets cancelled, epsilon gets cancelled, and this del Q del T will be current, but not the same current, because you see this current, because when you take this loop, This loop, you see, we have no displacement, no contribution coming from this term, because there is no variation of electric field here, right? Across this loop, across this surface, there is no variation of electric field, right? But when I am taking this surface, there is a variation of electric field across this surface, but there is no free current passing through this loop. So either of this term is contributing in these two cases. If I take this surface, then the first term is contributing. If I take this balloon-like surface, then the second term is contributing, and we get back the same result. So this ambiguity or this inadequacy of Ampere's law can be removed by including this term which was introduced by Maxwell. This is important because unless you understand this very clearly, it is difficult to appreciate the importance of the term. So this is the term which Maxwell introduced, and after you understand this, so let us now discuss about the propagation of electromagnetic waves across different medium. Right. Suppose we have seen that if it is a linear medium, the only difference is the speed of the electromagnetic wave is different, right? But suppose you have two different medium. One has suppose permittivity epsilon naught and magnetic permeability epsilon 1 and mu 1, and another one has permittivity epsilon 2 and magnetic permeability mu 2. And suppose the electromagnetic wave is going from one medium to other. So what are the physical phenomena that we expect to see there, right? Once it enters another medium, what are the things that should happen according to Maxwell's equation, right? So everything will be determined by Maxwell's equation. So here I have drawn two pictures to just illustrate the boundary conditions, right? So look at the first equation here, this d dot n ds. Again, this will be okay. So then you see, this is we have assumed a cylindrical pillbox. A cylindrical pillbox which is passing through the surface. So this rectangular region is representing the interface between the two mediums. Suppose this is one medium, this is another medium, and this is the interface. So we have assumed a cylindrical pillbox, right? So this portion, this shaded portion is basically lying on the interface, and this part is residing in the upper part is residing in the first medium, the bottom part is residing in the second medium. Now you see, if I apply the first this Gauss's law here, and if I take a flux, right, the flux of D across this closed surface, this is a cylindrical surface, right? Now one can basically choose any cylindrical pillbox, and if you decrease this height of the pillbox, if you gradually decrease it smaller and smaller and smaller in the limit delta h, this is suppose delta h is the height of this cylindrical pillbox. In the limit delta h tends to 0, the contribution of this side surface, right? This if you calculate the flux across this surface, it will be 0 because delta h tends to 0. So only contribution that will matter is the top surface and the bottom surface, right? So D perpendicular, so perpendicular component of D in the first mediums, D perpendicular 1, and you see, because they are on the opposite direction, the normal to the surface on the opposite direction, so that will be minus sign, is equal to sigma free. Why? Because the total charge, right? Sigma times A is the total charge enclosed in the surface. As someone stated that there's a mistake here, right? This is Q free. So when I integrate it over the area, so this will be D perpendicular 1 minus D perpendicular 2 times the area equal to charge density times the area. That will be the total charge. This would be Q free, right? So then you get this equation, this one, right? D perpendicular 1 minus D perpendicular 2 should be, so what it is saying us that the perpendicular component of the electric displacement vector is discontinuous at the boundary, and it is discontinuous by this amount, which is basically free charge density on the surface. And again, as you have learned that since this is a linear medium, so I can write D in terms of E in this way, epsilon 1 E perpendicular 1 minus epsilon 2 E perpendicular 2 equal to sigma free. So this is the first boundary condition coming from Gauss's law. Okay. And then if I apply the same thing for the magnetic field, you see the if I take a cylindrical pillbox and apply the same idea to the magnetic field, because we know that it's a I mean there is no magnetic monopole in nature, so we expect that this to be zero. So again we can reduce the height of this pillbox and make it zero. So only top surface and the bottom surface matter. The flux across this curved surface goes to zero. And similar in the same manner, you can write B perpendicular 1 minus B perpendicular 2 is equal to 0. The third one deals with again this. Okay, I have to come back to this picture. So here we are because the first two equation talks about surface, closed surface. The second two equation, Maxwell's equation, deals with loops, right? So here I have drawn again Ampere loop, which is basically threading across the interface. So this is again the interface. This is normal to the interface, and this loop is poking through this surface, right? So this is a closed loop, right? And if I basically take this loop and make it the width or this the height of the loop smaller and smaller and smaller, then what will happen? You see, in this equation we have this E dot dl, right? Electric field we are taking line integral along a closed path. You see, if I make this width very small tending to 0, so then the contribution for this to again they are on opposite direction, so again we are making them very small, so that goes away. And here you see upper one and the lower one, that parallel component of electric field on this side and on that side, they're on the opposite direction. So that's why they're on the opposite direction. E parallel 1 minus E parallel 2 equal to, why it is 0? Because you see, once I make this width very small, then the surface which is basically enclosed by this loop will be 0, because it is this surface, right? E dot dl will be del del t of B dot nds. So we are taking the flux to that this closed loop. So since the surface goes to 0, because the width goes to 0, so the term on the right hand side becomes 0. And then we have the fourth one, which deals with the current, right? What is the fourth one? This one, H dot dl equal to I free enclosed plus this. So again, you see, this is the perpendicular component, perpendicular to the surface. And suppose there are the width of the surface is very small, so there is no volume current as such. There is only surface current, right? And suppose you have placed the loop perpendicular to the surface current, because the surface current Kf is defined in that way. There is the amount of current which crossing like perpendicular to this surface. So the surface current, this is the line which is being crossed by this surface current Kf. So if you apply the same analogy where you decrease the height of this, so again the flux term, this will go to 0. There will be no contribution coming from this term, because you have decreased the width of the loop. So no surface area, so no contribution from the second term, only the first term remains, which can be again written in terms of the free current density. Okay, so free current density means Kf here. So you see Kf cross n, if you take a Kf cross n, what is that? It will give you this component, right? Kf cross n. B parallel by mu1, because this one, see, H is here, so H is B by mu. So that's why, and they are in the opposite direction. This and this are opposite direction. So B parallel 1 by mu1 minus B parallel 2 by mu2 is equal to Kf cross n. Now, what is this saying us? This is saying that the component of a magnetic field which is parallel to the surface but perpendicular to the current, surface current, that is what is discontinuous across the surface, right? This is not any arbitrary parallel component, right? I could have taken another parallel component that way or that way. It is the parallel component which is perpendicular to the surface current, that is discontinuous across the surface. So these are the four boundary conditions which must hold at the interface of two linear medium, right? There is no way you can escape this, right? These are basically coming from Maxwell's equation. And we basically shall apply this boundary condition while dealing with the propagation of electromagnetic waves across two different medium. Let us then discuss about this propagation of electromagnetic wave. Okay, I have to simplify this. Because suppose if you have a medium where there are no free charge or free current, naturally you see this free charge density is this and free current density is this. So suppose you have taken two mediums, say water and air, or say gas and say water, but there are no free charge density or current density. Naturally these terms will be zero, these terms will be zero, kf will be zero. So those equations becomes this, right? Because we have made that those terms zero. And these boundary conditions has to be used while basically solving the. You don't have to solve anything. Basically, you know the solution already. This plane wave solutions of electromagnetic waves, and you just apply the boundary condition and see what happens. There is nothing more than that. Very simple. So okay, let me just show you a picture. So in this picture, this surface. So this is x-axis. Perpendicular axis is the x-axis. This one is a z-axis, and the interface between the two medium is basically xy plane. Xy plane is the interface between the two medium. This is the first medium, which has a permeability mu1, permittivity epsilon 1. This medium has permeability mu2 and permittivity epsilon 2. So let us first imagine an electromagnetic wave which is coming from this side, from the left hand side, and propagating towards the plus z axis. So this from the transverse nature of electromagnetic wave, see the propagation vector k1, or this here it is vi, it is towards the plus z axis, the wave is propagating in this direction. And naturally E and B should be orthogonal to that, because you have seen that B can be obtained by k cap cross E by C. So this is perpendicular to this. So suppose polarization of the electric field, you can take any other direction of E as well. Here I am assuming that the incoming electromagnetic wave has polarization along the x axis. So EI incident, I for incident, EI is along x cap. And the propagation wave vector, suppose I call it k1 cap, and the velocity of the wave is v1, because velocity of the, I told you already that velocity of the wave in different medium will be different, right? Because the mu and epsilon are different. So in this side velocity is v1, in that side it will be v2. So EI, and this will be BI, magnetic field along the plus y axis, and this is the propagation wave vector. Now, okay, imagine a situation where this wave comes from this side and falls on the interface of the two medium. What will happen then, right? So the incoming electromagnetic wave, so there are two possibilities: either the wave will pass through and completely go into the second medium, or maybe a part can get reflected, or maybe a part can get transmitted, right? Or maybe the entire thing can get reflected. So let us see what would happen. In any case, the plane wave nature will be there, and the frequency of the electromagnetic wave will not change. I mean, the incoming wave or the outgoing wave or the transmitting wave, all of them will have the same frequency. Why? Because you see, the speed is different, right? So if the wavelength is different and the frequency is same, the speed is going to be different, right? Because it is a combination of frequency and wavelength. Wavelength basically is, so when frequency is same and the wavelength is large, the wave will propagate a larger distance, travel a larger distance, right? If the wavelength is small and the frequency is same, it will travel a smaller distance. So basically, the speed of the electromagnetic waves are different in the two medium just because they have different wavelength, right? Frequency is same. Now, let us write down the plane wave solutions for the electromagnetic wave that we have seen from the wave equation, right? So this is the electric field of the incident electromagnetic wave EI, and in this case, since I have assumed that the electromagnetic wave is propagating along the plus z direction, so that's why here I have written z instead of r, z and t. And as usual, this is a complex amplitude of the incident electromagnetic electric field, because that phase term could be inside this. And the polarization is written here. X cap is the polarization of the incoming electric field, incoming electric field of the incoming electromagnetic wave. And K1 is the wave vector, since it is propagating along z direction, that's why z is there, right? Minus omega t as usual. It's a standard solution, plane wave solution. And then if we try to get B incident from E incident, we have to use the same formula there, which we have discussed earlier. So 1 over C, here it is not C, it is the different speed, 1 over V1 K cap cross EI. What is K cap here? K cap, in which direction the wave is propagating? Z cap. So Z cap is basically K1 cap. K1 cap is the direction in which the wave is propagating. So K1 cap is equal to Z cap plus Z cap. So Z cap cross E cap, EI cap, EI, Z cap cross EI, and EI has a direction along X cap. So Z cap cross X cap is equal to Y cap. This is the direction. So the formula for B is equal to 1 by velocity times K cap cross EI, and we get this from this. In the same way, we can write down the plane wave solutions for the reflected component, because if you look in this picture, you see reflected means the wave. So again, I should emphasize that the entire thing which we are discussing here is applicable only for normal incidence, right? Because you see there is no angle of incidence. The wave is coming from this side and directly impinging on the surface, where electric field and magnetic field are orthogonal to the direction of propagation. So normal incidence, right? So it's not the most general scenario. It's a simplified version of the general thing. And so if a part of the electromagnetic wave gets reflected from the boundary, that must be traveling in the opposite direction, in the minus z direction, right? And what would happen to the electric field and magnetic field of the reflected wave? They will change. But see, E will not change because of the transverse nature of the electromagnetic wave. See, ER is again you can write in the same way. E0R is the complex amplitude of the reflected wave, and since the wave is propagated in the opposite direction, not at the plus z direction, minus z direction, so that's why it minus K1, because K1 cap was z cap. So now the wave is propagating along minus z cap, so that's why there is minus sign over there. And the polarization of the electric field remains same, but the polarization of the magnetic field, it will be in different direction, right? BR, because B can be obtained from E by using the same formula which we applied here, that is K cap here, K minus K1 cap, right? Minus K1 cap cross ER divided by V1, because it's the same medium. The reflected component is returning back to the same medium, so the speed will not change, speed will remain same. So minus of K1 cap cross ER, and ER has a direction along X cap, so minus of Z cap, because K1 cap is Z cap, so minus of Z cap cross Y cap, X cap will give you Y cap, so minus of Y cap, and in the denominator V1 should be there. And this is as usual, only difference is there is a minus sign there. And the part which is expected to be transmitted in the second medium, you see, in this case, the solution for the electric field will be written in this way, because it's a different medium. So this K2, instead of K1, we write K2, and the electric field vector is polarized along again in the same direction, X cap. And the speed of the wave in the second medium, since the transmitted part will be traveling in the second medium, the speed will be different. So V2 is there, so 1 by V, and then K2 cap cross ET. What is K2 cap? Again, it's same as the first one, incident wave, because transmitted part will travel in the same direction as the incident one. So V2, only the speed is different. Speed is different because the medium is different. Right? 1 over square root of mu epsilon. Here it is mu 2 epsilon 2. Here it is 1 over square root of mu 1 epsilon 1. So speed is different. That's why. But the wave vector is along the same direction. So in the same way, we can calculate Vt, which is 1 by V2. It is propagating along the positive z direction. So K2 cap equal to z cap. It's the positive sign here. And X, basically Z cap cross X cap will again give you Y cap. So these are the electric field and magnetic field associated with the incident, reflected and transmitted electromagnetic wave when an electromagnetic wave is incident at the interface of two linear medium. Once we have the expression for the electric field and magnetic field for all three components, we can straightway go to the boundary condition which we obtained from Maxwell's equation and plug in these expressions there in the boundary condition to see what happens. So let us first look at the first boundary condition. So suppose this, okay, so this is again for simplification. You can take any value of z, because once you make z equal to 0, your life becomes simple, right? Because suppose this xy, this boundary is suppose lying at z equal to 0. It could also lie at z equal to 5. That will only make your life complicated. So we just want to simplify our life. So z equal to 0, we have chosen it just to get rid of this exponential factor over there, because we have this exponential factor in each of the electric field and magnetic fields, right? And since the frequency is same, you see, frequency are same, right? If I make z equal to 0, then this term goes away, right? The term is not there. So there should not be any speciality of the surface. This is just only for simplification. So z equal to, so we imagine that this surface is lying at z equal to 0. And when we apply the first boundary condition, you see the first boundary condition was parallel. It is not the first one, maybe I should, this one, right? Which one? Parallel, this one. This is the third one. Okay, maybe I have written the other way around here. E parallel 1 equal to E parallel 2. So for the parallel component, if I write the parallel components in the first medium equal to parallel component in the second medium. Now the parallel component of electric field on the left hand side, you see there are two waves. Wave number 1, wave number 2, because it's the incident. There are two waves on the left hand side in the first medium. One is the incident wave, another one is the reflected wave. So we should actually sum, because the parallel components of the electric field of both these waves. So that's why you have written here E0I, the complex amplitude of the incident electric field plus the complex amplitude of the reflected electric field should be equal to the complex amplitude of the transmitted electric field. But remember here, all these are parallel component. How do I write this? Because you see there are no perpendicular component. If you look carefully, because this is a special case, normal incidence, there are no perpendicular component. Electric field is entirely parallel, tangential to the surface here. Right? There are no perpendicular component. So two of the boundary conditions become redundant. You don't have to deal with these two boundary conditions. Look at this. Right, E perpendicular. There is no E perpendicular, so 0 equal to 0. And there is no perpendicular component of B as well, so 0 equal to 0. So we just throw away these two boundary conditions, because you don't need it in this situation. We just need only these two boundary conditions in this case. The first one that I have used here, the third, or rather the third one, E parallel 1 equal to parallel 2, that gives us E0I plus E0R equal to E0T. And then the fourth one, which was basically this one, B parallel 1 by mu1 equal to B parallel 2 by mu2. So if we use this boundary condition, you see the amplitudes are related in this way. So B parallel 1 is basically E0I by V1. Look at this. You see, this E0I, this is E0I by V1, right? Since we have put Z equal to 0, that becomes 0, right? This term goes to 0. And since omega is same, we have thrown away the terms from the both left hand side. That becomes e to the power minus I omega t, e to the power minus I omega t, which you have thrown away, because they are same for each and every terms here in the both side. So in this case, so B parallel 1 will be E0I by V1, and B parallel 2 will be negative. You see, I have seen this, right? It's negative, because it is moving along a different direction, just opposite direction as compared to the incident wave. So that's why there is E0R by V1 is equal to, so there are two parallel components, one for the incoming wave, another for the reflected wave. We have combined them both. In this case, they were in the same direction. In this case, they are in the opposite direction. You see, if you look at the picture, you can see the magnetic field for the incoming wave is along the plus y direction, while the magnetic field for the reflected wave is along the minus y direction. So they are in the opposite direction. So the parallel component of B at the interface for the incoming and the reflected wave are in the opposite direction. That's why there is a negative sign here, right? And if you simplify this, mu1, v1 is same for the incoming and the reflected wave. So we can take that outside this bracket. And if I write this, mu1 v1 by mu2 v2, mu1 v1 by mu2 v2, again V can be written in terms of reflective index, because you know reflective index is defined as n equal to the speed of light in vacuum divided by the speed of light in that medium divided by the speed of light in vacuum. So they are inversely proportional. So V equal to C by N. I just told the opposite. V equal to C by N, speed of light in vacuum divided by speed of light in that medium, C by N. So V1 inversely proportional to N1. So that's why mu1 V1 by divided by mu2 V2, one can write mu1 N2 divided by mu2 N1. And this beta, so in that side, so you have two equation, E0I plus E0R equal to E0T. These are the complex amplitudes. And E0I minus E0R equal to beta times E0T. You just have to solve these two equations. Simple. Okay. If you solve them, we get the reflected and transmitted components of the electric field in terms of the incident, because you know the incident, right? We do not know what is the reflected component or the transmitted component. We are trying to calculate that from the Maxwell's equation, because Maxwell's equation gives us some boundary condition. We have plane wave solutions. We are applying those boundary conditions on the plane wave solutions, are getting these amplitudes for the reflected and the transmitted wave in terms of the incident electric field amplitudes. And beta is this. Now let us see. Again, this is for a linear medium. So if you take, say, water and air or water and glass, they are basically non-magnetic. So magnetic permeability will be almost equal to the magnetic permeability of vacuum. So mu1 equal to mu2 equal to mu naught. So you can write beta equal to v1 by v2, because mu1 equal to mu2 equal to mu0, that gets cancelled. So beta equal to v1 by v2 equal to n2 by n1. How much time? Okay, still 10 minutes, fine. So now we have already obtained these expressions for reflected electric field and transmitted electric field, and they are complex, right? You see, the tilde sign is telling you that these are complex things. Now see what we do with the complex things. We want the real amplitudes, right? So the real amplitudes will be if we take mod of that, so E0R will be simply, so beta is simply v1 by v2. So this will be v2 minus v1 by v2 plus v1 E0I, and reflected component can be also written in terms of n1. So it will be opposite n1 minus n2 by n1 plus n2 E0I. So these are the relationship between the real amplitude of the reflected electric field and the incident electric field. Similarly, you can again write down the same for the E0 real amplitude of the transmitted component, which is 2v2 by v2 plus v1, straightforward to get these expressions from these two equations. So E0t equal to 2n1 by n1 plus n2 E0I. Now what are the things that these two equations are trying to tell us? You see, if you look at the first one, you see there is a possibility that this can also become negative, right? Because v2 minus v1, depending on the value of v1 and v2, this can be positive or negative. But in this case, it will be always positive, right? There is no minus here. So this will be always positive. That means the transmitted electric field will have the exactly same phase as the incident electric, irrespective of the condition, whether it is going from a rare medium to denser medium, or whatever medium it is going on, they will have the same phase. But here there is a possibility that if so it is telling us that v2 is greater than v1. V2 is greater than V1 means second medium velocity is high. That means going from the denser medium to rare medium. So the second medium's reflective index will be smaller than the first medium, right? In that case, E0R and E0I will be in phase, because V2 is greater than V1. So it's a positive quantity. They are in phase. But if opposite is the case, when it is going from so V1 is larger than V2, right? V1 is larger than V2. So that means you are going from a rare medium to a denser medium. If that is the case, then V2 minus V1 will be less than 0, and it will be negative. So it is telling us that E0R is 180 degree out of phase with the E0I in that case. And probably you have learned this in your physical optics in your BSc course, that whenever a light is incident from a rare medium to denser medium, there is a phase change of pi. during that, right? And you can see that this is nothing but Maxwell's equation. It is not something, some fundamental law. It's Maxwell's equation. Maxwell's equation tells us that that has to happen, right? Otherwise, boundary condition will not satisfy. And boundary condition is nothing but Maxwell's equation, right? If the boundary conditions are violated, Maxwell's equations are violated. And there is no way Maxwell's equation can be violated. So, because those are fundamental laws. So, this phenomena, there is a phase change that is because of this. Okay. Now, let us get back to the discussion on the intensity. Okay. So, what is intensity? Intensity is basically amount of energy crossing per unit area per unit time. You may ask me then what is the difference between the Poynting vector and this, right? Amount of energy crossing per unit area per unit. So wave is propagating in any medium. So suppose imagine cross sectional area of 1. So area equal to 1. And if you multiply area equal to 1 with the speed of the wave, you get a cylinder, right? V times area. So area is 1. So V1, it could be V2, it could be C, anything. So it will be the volume of cylinder. Now, if you multiply the energy density of the electromagnetic field with that volume, you get the total energy passing through that surface per second, right? Per unit area, because you have chosen area to be 1. Right. Now, why this is so? Because you see, we have already learned that the energy density of electromagnetic field is half, and E, you can again simplify it to get, it will be epsilon square. Epsilon is square simply because b square by mu 0 can be again converted to epsilon and E, written in terms of epsilon and E. So it will be half epsilon square plus half epsilon square, symmetric. The energy is shared equally. They are democratic. Electric field and magnetic field, they have equal energy density. And if you sum them, you get epsilon square. And if you multiply with area, you get area is 1 and velocity is V. So you have epsilon square times V. But why this half factor is over there? Because you see E equal to actually E0 cos omega t or sin omega t, the real part if you take, right? And if you take a time average of that, it will throw out a factor of half sin square or cos square omega t, time average, right? So that's why this half factor is there. So this is intensity, amount of energy crossing per unit area per unit time, right? And if I compare now the intensity of the incoming electromagnetic wave with that reflected wave or the transmitted wave, what do we see? So reflection coefficient is defined in this way. This is simply the intensity of the reflected wave divided by intensity of the incoming wave. Now you see same medium, so epsilon is same, epsilon 1, velocity is same, v1, that these things gets cancelled. So we have to just take a ratio of E0R by E0I and a square, because there is a square here. And we have already learned that E0R by E0I is basically what? E0R by E0I, N1 minus N2 by N1 plus N2. So it is simply N1 minus N2 divided by N1 plus N2 square. Fine. So if you know the refractive index of the two medium, you can easily tell what should be the reflection coefficient. Similarly, if you want to calculate the transmission coefficient, that has to be T has to be IT by I, intensity of the transmitted wave divided by intensity of the incident wave. Now, the waves are traveling in two different medium. Transmitted wave is traveling in the second medium, incident wave is traveling in the first medium. That's why this epsilon 2 V2, you see epsilon 2 V2, and the denominator epsilon 1 V1 and E0T by E0I square. Right. Again, we know what is E0T by E0I. Right? E0T divided by E0I equal to twice N1 divided by N1 plus N2. So if you put them and simplify, you simply get this one. Right. Again, you see epsilon 2 V2 and V2 and V1 can be written in terms of N1 and N2. Right. So finally, if you simplify them, you get 4N1 N2 divided by N1 plus N2 square. So these are the expression for reflection coefficient and transmission coefficient. In case of normal incidence of electromagnetic wave at the interface of two linear homogeneous medium. Let us take one example here. How much time we have? Okay, not much, 2 minutes, fine. So suppose we are taking air and water. So air has a reflecting index of 1, water has a reflecting index of 1.5, If you plug those numbers here, what are the outcome? It is telling us that R will be only 0.04, T will be 0.96, right? Sorry, this is water, right? So this is suggesting that only 4% gets reflected. Am I writing this correct? Water, it is 1.5, right? I don't remember it exactly. Maybe 1.5. I think so. এটা গ্লাস হবে মনে হয়, রাইট? 1.3 হয় ওয়াটারের, আমার যদি মনে পড়ছে, আমি এটা ভুল করে লিখে ফেলেছি, রাইট? So this is not a water, it's a glass, right? N1 equal to 1 for air, and for glass এটা water হবে না, সরি, this will be গ্লাসের জন্য, নরমাল গ্লাসের জন্য 1.5 হবে এটা N2 টা। তাহলে if we consider air and glass, not water, sorry, so then you expect that only 4% of the light should be reflected, and 96% should be transmitted in the second medium. So if I take air and glass as two medium and send an electromagnetic wave from air to glass, only 4% gets reflected, 96% gets transmitted. So you can make such beautiful prediction based only on Maxwell's equation, right? Maxwell's equations allow you to make such prediction that how much light will get reflected and how much light will get transmitted. Now, can you tell me, when you stand in front of your mirror, do you see such things? If only 4% gets reflected, can you see your face in the mirror? Mirror is a glass again, right? And mirror is a glass. So light going from your face to the mirror, and then only 4% gets reflected, right? Okay, I will discuss this because you have not maybe have not learned this in the previous semester, because that was the propagation of electromagnetic wave in conductors. If you take conductors, what happens? You see, if you look at a mirror, the back surface of a mirror, you will see a nice thin coating of mercury, right? It's a very good conductor, a thin coating of mercury, and basically this mercury, whenever electromagnetic wave gets incident in a good conductor, like anything like copper or say silver or mercury. I think mirror it is silver or mercury, any of them, right? So since they have a very good conductivity, what happens that when electromagnetic wave tries to propagate through a conductor, they gets attenuated very fast, exponentially. And there is something called skin depth. Each and every conductor, right? Skin depth, because I mean the distance over the amplitude of the electric field falls away by a factor of 1 by E, is called skin depth. So the better the conductor, the higher the conductivity, the smaller the skin depth, right? So if you have a very good conductor, you need a very thin coating of that on the back side of your mirror. So what happens that the transmitted component is completely attenuated, right? So that's why everything is getting reflected. That's why you can see your face in the mirror, right? But not in front of a normal glass, right? Because you have glass in your window. You can, if you stand there, you will not be able to see your face clearly, but you can see it in front of a mirror. Another interesting application that comes to my mind is that, you see, the reflection and transmission coefficients are very useful, particularly in case of deciphering this satellite images. You must be aware of this Google, what is that? This Google provide Google Maps, right? You can have satellite images of different regions. You can see the forests or the rivers or the roads from a satellite, right? But how do you decide whether say Green Valley is a paddy field or something like a forest or something else, right? You have to decide based on the reflection coefficient. Because once you calculate the reflection coefficient and transmission coefficient, you can immediately tell whether that's a paddy field or that's a river. Or suppose river and road, they look like same from a satellite image, right? Almost same. I mean, maybe you can decipher it, but if you look at that wiggly curve, it may be a road, it may be a river. But if you calculate the reflection coefficient, transmission coefficient, because in one case it is the electromagnetic wave is impinging on the soil. Another case it is impinging on the water. So R and T will be different. So once you analyze that, you can tell me with a conviction that whether it's a pond or a river or a road or a paddy field, right? So that's a nice application of this. But in any way, I mean, this is a general thing which can be applied anywhere. And today we have only discussed about the normal incidents. Okay. In the next class, we will discuss about the oblique incidents and maybe some part of this conductor, the electromagnetic waves in conductors. So I stop here, okay, because the time is over. If you have any questions, please ask. Can you hear me? Hello?
Yes, sir.
Hello? Okay, okay. Okay, if you have no questions, then fine. We shall again meet on Friday. We have a class from, I think, 1:30 to 3:30, right? So unless I tell you that, see, some of you may have some doubt whether the class will take place or not. So unless I separately mention that I will not be available for the class on a particular day, you can simply assume that the class will be held on the scheduled time, right?
হ্যালো স্যার, হ্যালো স্যার,
Yes, yes, yes. I can hear you.
আমাদের 2 ঘন্টার ক্লাসগুলো 1 ঘন্টা করে নিলে স্যার ভালো হয়।
আমি বুঝতে পারছি, কিন্তু এখন দেখো রুটিনটা তো আমি বানাইনি, যা দিয়ে দেওয়া হয়েছে আপাতত হয়তো ম্যানেজ করা যেতে পারে, কারণ ল্যাব ক্লাসগুলো হচ্ছে না, রাইট? সেটা আমার জন্য ভালো হয়, কারণ তোমরা হয়তো জানো না যে আমি একটা হেলথ প্রবলেমের মানে জন্য আগের সেমিস্টার তোমরা ক্লাসটা নিতে পারিনি। সেটা গলার সমস্যাও আছে আমার, টানা 2 ঘন্টা বলবে আমারও প্রবলেম হয়, মানে ভয়েস চোক করে যায়। তো ভোকাল কর্ডে একটা সমস্যা আছে আমার, রাইট? সো সেটা হলে আমার ভালো হয়, কিন্তু এখন আমি দেখি কালকে ডিপার্টমেন্টে যাব, আমি এইচওডির সঙ্গে কথা বলবো, যদি সেটা অ্যালাউ করা যেতে পারে তাহলে নেওয়া যেতে পারে, কারণ এখন আপাতত মধ্যে এক্সপেরিমেন্টাল ল্যাবগুলো তো হচ্ছে না, সেই সময় যদি নেওয়া যায়। কিন্তু যদি কোনো অবজেকশন থাকে তাহলে আমাকে রুটিনই ফলো করতে হবে। আশা করি হয়তো অবজেকশন হবে না, কাল কথা বলে দেখি, আমি যদি হয় তাহলে তোমাদের সঙ্গে কথা বলে তোমাদের সুবিধার মতো একটা টাইম ফিক্স করে নেওয়া যাবে, ঠিক আছে? ওকে ওকে তাহলে ঠিক আছে, সি ইউ অ্যাগেন অন ফ্রাইডে।
স্যার,
হ্যাঁ বলো বলো।
বলছি এই পিডিএফটা কি আজকে একটু পাঠিয়ে দেবেন হোয়াটসঅ্যাপে?
হ্যাঁ হ্যাঁ পাঠিয়ে দেবো, কয়েকটা জিনিস কারেক্ট করে পাঠিয়ে দেবো। ওই যে আমরা বললো না, টাইপ করতে গিয়ে সিগমা ফ্রি রেখে দিচ্ছি কিউ ফ্রির জায়গায়। তোমরা আমাকে যদি আমি পাঠিয়েও দিই অনেক সময়, হ্যাঁ তোমরা একটু দেখে নিও, কারণ যেটা হচ্ছে এটা খুব তাড়াতাড়ি করে করা তো, একদিনে বুঝতে পারছো, হয়তো ঘন্টা 2 বসলাম টাইপ করলাম, কোথাও কিছু টাইপও থেকে যেতে পারে। সুতরাং তোমরা যদি কখনো কোনো টাইপও নোট করে থাকো তাহলে আমাকে পরে জানিয়ে দিও, ঠিক আছে? আমি আজ এটা আপলোড করে দিচ্ছি, ঠিক আছে? ওকে
ওকে
ওকে ওকে।